Today, I am joined by Arthur Breitman, co-founder of Tezos. We're here to talk about TzEL, an experimental project exploring private post-quantum payments on Tezos testnet. The question behind it is simple. If public blockchain data can remain available indefinitely, what would it take for private transactions to stay private years from now? Arthur, thanks for joining us.
Thank you for having me.
It's our pleasure. Most people think about blockchain privacy as a present-day question. Can someone see this transaction right now? But public blockchain data can stick around indefinitely. Is the right starting point here that blockchain privacy has a time problem?
So the answer is partially yes. And I used to think that it didn't. And let me explain a little bit. So most of the systems which have been used to provide privacy on blockchains have relied on zero knowledge proofs. And in a zero knowledge proof, the zero knowledge part that you get, it comes from information theory. So the information is just not there. It's not encrypted in a way that you can't find it. It's just not there. And so it doesn't matter if you have quantum computers or whatever you have, the laws of physics tell, or not even mathematics, tells you like you can't access it. So I thought, because this is all safe, you might be able to forge fake proofs in the future, but you won't be able to see the data. And the picture is a little more complex than this, because when you make those transactions on most systems today, I don't just go and tell you, hey, by the way, I've made a transaction, and you should check your balance. You have a transaction. For convenience, an encrypted memo is added to the blockchain. And it's way more convenient like this, because I don't have to if I receive a payment from you, I don't have to give you my email address. I don't have to give you a way to reach me with information. I can just receive it. That's important. But it means you have an encrypted memo that sticks around. And that memo is encrypted with a key that can itself be cracked by quantum computers. So if you look at a system like the sampling circuit on Tezos today, and of course sampling came from Zcash, so it applies to Zcash as well. It's not as bad as, oh my God, everything is going to be decryptable. The scenario is the following. If you know someone's public key and you have a quantum computer, you'll be able to decrypt the memos, which is why usually it's recommended to not reuse your public key, give every single person a different public key. It's not always practical. People don't always do this. And so unless you have really, really good hygiene today in using the systems, there's a risk that if someone with your public key and access to quantum computers, maybe not next month, maybe in 10 years, maybe in 3 years, can decrypt those messages.
Permanence is the part worth staying with for a moment. If encrypted private transaction data remains part of the public record, privacy has to be judged across time, not only at the moment the transaction happens. So what does it mean for a private transaction to have a long memory?
Well, that's the thing. Is every transaction on a blockchain is essentially broadcast publicly, and the trick to it's an abnormal state of affair, right? Before blockchains, there are no system in which all the transactions are public. It's kind of weird, and privacy preserving solutions on blockchain restore some normalcy, right? What they do is say, look, we're going, if we're not going to broadcast it for everyone, we're going to encrypt it. And then because it's encrypted and we still need to check that it's valid, we'll have a proof that it's valid. So you'll have an encrypted transaction with a proof that it's valid. And that can restore a little bit the status quo. What would you expect out of a normal payment system? It's not a radical thing. It's a fairly normal thing to do. Although it's been framed a bit differently. Now, on a blockchain, typically, if your information is public, the fact that it sticks around forever doesn't really make a difference, because I would say as long as your information is public once, we should assume it's going to stick around forever. You should not, your privacy should not rely on the fact that someone is going to kindly delete the data. Uh, and it gets a bit different once you start talking about data that is encrypted. There's a concept that people talk about for quantum computers called harvest now, decrypt later, where an adversary could, get a bunch of encrypted messages and they can't decrypt them now, but later on with quantum computers they have access to it and they can decrypt it retroactively. And usually it's not really a problem that blockchains have, because in general there is nothing to decrypt. Right. The problem that blockchains have is at some point in the future you can forge transactions, but as long as you migrate before that, the old transactions are what they are. They're not going to change. They're in past blocks. They're done. So as long as you migrate to your keys, you'll be fine. It's a bit different once you start having encryption come into play, and that's where like the privacy preserving systems do involve some encryption, and so to some extent they are subject to this harvest now, decrypt later problem.
Well, this turns a general cryptocurrency concern into a specific engineering problem. Private payments, long term data exposure, post quantum assumptions, and a roll up based implementation. What made this problem interesting enough for you to work on personally?
Oh, I mean, it's super interesting to begin with. I think it's a really interesting engineering challenge to begin with. It hasn't really been done. I think I don't want to make a blanket statement because a lot of people are doing a lot of crypto projects. I haven't heard of any crypto projects having quantum resistance privacy. There may be some tests out there, and TzEL itself is only a test net right now, so it's not in production. Um, but I wanted to challenge myself a little bit. And I also thought that part of the problem with those systems is that the proofs from post-quantum systems are a bit heavier than what you can get with a lot of like the elliptic curve family of constructions will give you more efficient proofs. So because they're a bit heavy, people have considered that this was not very practical. But then I remember that Tezos has a DAO, that availability layer, that actually lets us put a lot of the data you don't really need to know what to do on a blockchain, but to check that it's valid. And that's exactly what a proof is. And so I figured, wait a second, we can actually put those proofs on the DAO, the data availability layer. And because we have this, it makes it like a really interesting fit. I also wanted to, I've been doing more agentic coding as of late. It's given me an opportunity to go back into and find the time to actually do direct contribution, and it was quite interesting. I think there's a misconception that if you use agentic coding, somehow you're going to make a lot of bugs and have all these problems, and it's certainly possible to fall into that trap. I don't think it works like this. I think what it does is that it makes it a lot easier to develop. And there was actually this is inspired by something like Vitalik Buterin was actually saying this morning, but I think it's completely true. It's like it made programming with bugs went from normal to extremely easy, and programming with a high level of security came from extremely hard to now just moderate. And I think if you use the right approaches, in particular if you use you can use tools for informal verification, you can do multiple separate implementations. You can rely on very, very strong unit tests. So if you have all of this knowledge of good security practices for writing robust code, you can actually elicit really, really strong systems out of it. I also wanted to be more familiar with some of the post-quantum proving tools that exist out there. And part of this also stemmed from a general push that or drive that I've had to really try to figure out the post-quantum situation for Tezos. So I would think I don't think there's not a lot of people using the sampling tools that are available on Tezos. So this is not a burning need. More pressing is converting Baker signatures into post-quantum signatures and having aggregation around it. The DAO itself, the DAO itself also needs to be moved to a post-quantum system. We have some pretty good ideas on how to do this. I wanted to become more familiar with it, and so I've been making experiments. So TzEL now is available as a testnet. It's something that can be used, but Actually, I spent quite a bit of time on adaptability layers and proof aggregation for bakers as well, which is less visible, less fun, but probably a bigger priority as well.
The less visible updates, we find ourselves often going, "What's going on?" We only feel the work, we never see the results, but we do appreciate them. So thank you. Post quantum cryptography makes long term protocol design very concrete. The assumptions underneath the system can change. Does post quantum cryptography make the need for long term protocol adaptability more concrete?
It does. I mean, I think that need has always been present. And to a large extent, I would say a lot of protocol designs have converged. I think there's like a consensus. Well, among a small group of people, there's a consensus as to what constitutes a good design for a blockchain. Uh, that consensus is not reached like Solana, for example. But there's a group, among like I would say like blockchain researchers. I think there's a general idea on how to scale. So to some extent, when I started working on Tezos, there was a lot to be discovered, a lot to be done. It wasn't even clear how to do proof of stake. It wasn't even clear what form smart contracts should have. A lot of these questions have been answered, but for the longest time, post quantum was a big one, and it's one that everyone will eventually have to face. Once you have like systems that completely scale and are post quantum, will there be problems that you need to? Yes, probably. They're harder to foresee. I think you always need adaptability. The difference is that at one point, the problems you were going to have were kind of foreseeable. And then, once you have systems that completely scale, are private, are secure, and are, quantum resistant, we don't know what the topics will be.
The claims around
Sorry.
Oh, you're fine. The claims around TzEL need a careful boundary. People can hear post quantum or private payments and run too far with the claim. What should people be careful not to claim about TzEL?
Oh boy. Well, first of all, that is production ready. I think it needs there's been quite a bit of work actually going on into like ensuring the security of it, but it's still proper audits. It still needs proper integration into wallets before it can be used on chain. There's also the fact that whilst the entire system is post quantum, one solution to the decrypt now and harvest later problem would have been to not make the entire system post quantum, but just the encryption part. So like just the part where you encrypt it.
Oh no!
Oops, sorry, I dropped. Can
You're
you
fine.
still see me?
Yes.
Yeah. So I was saying one possibility would have been to just do the encryption part in a post quantum way, and not the whole rest. It was interesting, right? As a bit of a proof of concept to say like, can we do the whole stack post quantum? With that said, it runs as a rollup on Tezos, and which itself has a not post quantum architecture. It still has like elliptic curve for Baker signatures. The DAL itself relies on the KZG proof. So whilst like by itself is fully like quantum resistant, it runs on a non-quantum resistant system. So that's something to bear in mind. So it's definitely about starting to get familiar with this technology and demonstrating it, getting used to it. It was also a way to experiment with like different technologies around like what is a good circuit for shielded transactions. So there's a lot of good ideas in sapling, like viewing keys, like inbound viewing keys, outbound viewing keys, delegated proving. There were others that came from other circuits. So Penumbra had this concept of detection key, where you can scan the blockchain and see if a transaction is probably yours or like probably of interest to you, but you don't know anything of the content. And that's very useful if you have like a wallet service. You can just give it this key and then say like, hey, you might be interested in this. And then you can take it and look at it, as opposed to give them a full viewing key. And yeah, at some point, like you can start building all this like Legos. And it's really interesting to be able to like construct the circuits and have all the properties you want.
A working prototype can be valuable without being a finished product. It can show a design path is real while still leaving review, testing, and hardening ahead. What does
Yeah.
this prototype prove, and what does it still leave unproven?
Well, one, it proves we can do it. Two, it proves intent and interest in doing it. I think a lot of people are not going to bother doing this, and this is, I think something that at some point should be a part of Tezos X, in the same way that, if you wanted to create shielded transaction as part of a smart contract on Tezos, you've been, able to do that for a few years. That should remain possible on a post-quantum system. When we've discussed transition to post-quantum, we identified the list of, I say we, different core teams working on a Tezos protocol have identified the parts that you need replacing, and there were signatures for transactions, aggregation of signatures for bakers, the adaptability layer, the randomness generation from the VDF, and then certain mechanism primitives like sapling. So that's a drop-in replacement for that, and some time lock puzzles, which are barely used. So I don't think this one is like a big priority. So this is like one brick out of what comes.
So, what had to be built for this to become sort of an end to end system rather than just a paper design?
Tezos has to be built. That's the thing. It's like we had to have that adaptability layer. We had to have a L1 blockchain. We had to have a rollup stack. But it is interesting. It is exciting that it is actually like now quite pragmatic to go out and like build a rollup kernel. I just that just works, and there's extremely good documentation for doing it. There's a lot of good code examples. So you can build your rollup kernel now and try a lot of things, and you have you have the infrastructure in place to do it. But internally, the parts about it are essentially there are the circuit parts, which are about like making the proofs that you want to make, a bit of wiring around the proofs and around encryption of nodes, a bit of infrastructure around like how to send transactions, how to have like remote provers, and a bit of smart contract code to do bridging of assets between L1 and a rollup.
Now, once something becomes a running system, the clean design meets friction. Some parts get harder, some parts get clearer, some assumptions get tested in ways a spec can't fully show. What did you only learn once this became a working prototype?
Mm. I mean, there were learnings around the way. Like I made some mistakes and I fixed them and realized like I had like thought of it like sort of certain things in the right way, sort of other things in the wrong way. Uh, but I don't think at the end there was like a particularly like salient lesson. It's like the small lessons, but the lessons are the fact of like, yes, you really need a two-phase commit for bridging. Otherwise, your tokens can get stuck on the bridge. Like this type of like bug that are like that you can make easily with a rollup. So like very lessons very specific to rollup construction and not like particularly of general interest.
Perfect. Well, proof size is one of the hardest constraints here. Post quantum friendly privacy can bring heavier proof data, and larger proof data changes when the system needs it underneath. Why does proof size matter so much on a blockchain?
Well, on a typical blockchain, if you don't have a adaptability layer, everyone needs to download all the data. And so, the proofs are about 300 kilobytes per transaction. And so if you only have like 10 transactions per second in a system like this, that would already be 3 megabytes per second that everyone has to download. If you have 100 transactions per second, that's like 300 megabytes. So it's too much to put on a layer one. It's far more appropriate to do this on a adaptability layer, because what the adaptability layer does is that it shards this responsibility so that many people download small pieces of the data and can reconstruct it together. It still requires a rollup operator to download all the data. But, or any rollup operator, it's not a single operator, but anyone running a rollup node needs to download all of the data. However, that's fewer people, and they may have more performant hardware, more performant bandwidth in order to do that.
What does the Tezos DAO change about the design space?
I think it opens it up to systems which need more data to run, like more witness data, bigger proofs, these type of things. And what people have contemplated in the past is doing proof aggregation. So where you'd have like a rollup, a rollup sequencer, which does more than sequencing, which also takes the proofs, aggregates them, and then posts an aggregated proof. But that gives a lot of like power, not so much power, but it gives a lot of importance to that sequencer. There's no sequencer right now in this in TzEL, and I think like people can be shy to be a sequencer for a system that does shielded, that purely does shielded transactions.
Yeah, that's fair. This also raises the question: TzEL puts heavier cryptographic work in a rollup rather than forcing every detail onto layer one. Is this the broader pattern? Heavier cryptographic systems run in rollups, while the Tezos protocol provides settlement and data availability?
So the load isn't that much. Like verifying a proof is fairly fast. It's not as fast as verifying a signature, but it's not massive. Like the computational cost is really on the side of the prover. Like building the proof takes a lot of RAM, takes a lot of CPU. Verifying the proof is fairly fast and fairly easy. But in general, I would say it's all computation, all of that can go on. Is much more efficient to put that into to construct it at the layer 2 system rather than at the layer 1 system. So like a clean separation is that your layer 1 focuses on consensus and staking. So that gives you a platform where you can like basically timestamp your and decide it and data availability. So you can say like at this point, like this blob of data was available. And then behind that, you have systems figure out like where the data is, download the data, execute the data, do all of this. But the point is like you need a single honest participant to do this. Whereas on a rollup, you would need like, sorry, not on L1, you need an honest majority. So like for the L1, you want to be more conservative. You want people to, you want the validators to do less, to really focus on like the underlying security of the system, less so on the performance. So it's kind of like, you separate your security and your performance, and that's a really elegant way to scale.
Private payments still need practical controls. Users need ways to detect payments, recover information, and reveal specific details when needed. How should people think about viewing keys, detector keys, and selective disclosure in a private payment system?
Yeah. So, there's the version of all these protocols where you don't have viewing keys, you don't have any of this. Everyone just runs a node that always listens to the blockchain, and that's all that happens. And that's not very practical if you're not always online, if you want to use a wallet on your phone, if you do different thing. And I think that was one bit of Zcash early on that was really inspired, was thinking through all these different keys and all these different delegations that you might need. And you have this idea of like a master key that gives you that lets you do everything, and then you can derive and devolve like small powers to different parties. So the idea of the viewing keys, for instance, is like, look, you don't want to listen to every single block on chain. So you could give someone your viewing key or give a wallet your viewing key without your spending key. Maybe your spending key stays on the hardware, and like your computer only has your viewing key, but then it can download all these transactions and tell you they're yours. If you have a detection key, you can even do something a bit better. You have a service you give the detection key to, and with some error rate, you say like, oh, maybe that transaction is yours, right? So you get a subset of the transactions. Then maybe you have another service which has a little more, which has your viewing key, and say like, oh yeah, that's what's happening here. And then you can spend and you can do all the things. So it really lets you use external services, but only give like a minimal amount of power to these services. Likewise, there's a possibility to use an external prover. I think that's important because the prover does take a lot of CPUs. Like on a beefy machines, you can do the proofs in seconds, but they will still take like loads and loads of RAM, more RAM than people might have even on a laptop, for example. So if you want to use an external prover, that maybe you're going to disclose some stuff to the prover. The prover might know what the transaction is, but you don't want the prover to be able to spend your funds. So you only trust the prover not to go around and like tell everyone a statement that they proved, but not to not spend your money. So like again, that's a proving key. In terms of the selective disclosure, I think it's also, and this is again something that was introduced by Zcash culturally, this idea of thinking about privacy not as hiding, but as selective disclosure. And that's the default. When you have documents, in your home, when you have emails, all of that, they're not like hidden. It's just that it's selective disclosure. You choose who you're going to disclose to. And legal systems are completely already well equipped with dealing with this type of information. It's called a subpoena or it's called discovery. If the police thinks you've done something wrong, and they can go to your they can go to your email provider and try to subpoena the emails, for example, or they can they can. So in the US, for example, it's the legal system most people are familiar with because of movies and TV shows. If they've not been familiar with their own legal systems, because they may not have faced it. But like you'll have this thing where you say like, well, you might not have to testify against you, but like if you want to defend yourself, you better be able to like actually like show up evidence, and so you have to disclose these things. That's the concept of selective disclosure. You choose who you disclose to. And even from a regulatory perspective, you can think of regulation this way. You can tell people like, look, maybe you get audited. For example, you get a tax audit, and they might come and say like, well, you have to show us
say those words, sir. Never
you have
say
to show,
those words.
well, it's very it's a very it's like it's very high stake paperwork. It's very annoying. I've had tax audits. It's not pleasant.
Worst.
It just takes a long time. I do have a note on this, but I'm gonna put a pin on it. But let's say this happened. Yeah, they can make you disclose it when you see your transaction. You show your key, and on a blockchain, it's weird because on a blockchain, by default, you disclose it to everyone. And so I think this notion of selective disclosure is important to get people to understand that there's nothing weird about the privacy. You're not hiding it. You're not hiding it. You're saying like, no, I'm just like not giving it to everyone. And if you want to know what the transaction is, and you have a legal right to know, then you can go and assert that legal right, and then you can compel me, and then you can either like put me in contempt of court for not showing my key. You do whatever you want, but like by default, you're not just going to like force me to like broadcast it to the entire world to see. And I think that's like a very reasonable way to look at the question. On the tax audit side, assuming
taxing.
Assuming first of all, it's very silly to cheat on your taxes. Don't do it. It's not worth it. But with that said, even if you've done everything right and you get audited, it's still a massive pain in the ass. The thing that's really useful though is like coding agents really, really good at chasing paperwork throughout your inbox and through your documents. And a thing that used to be extremely painful in terms of like chasing everything, like finding all the receipt, finding all of this, you can now do it for a fraction of the cost and a fraction of the time. And so I think that reduces the pain immensely if God forbid it happens to anyone.
Are you using Claude Code? Are you using OpenClaw, Hermes Agent?
No, I use mostly Claude Code and Codex quite a bit, and with some frameworks that I have around them.
Okay, interesting. Yeah, I'm just curious what you. Sorry, aside.
No, I mean it's that's the thing. It's like people think of them as coding agents. They're actually quite good at admin tasks and chasing paperwork.
Right. Yeah. I'm seeing like I think Anthropic just dropped a legal skill for Claude recently. So there's.
Yeah, but without even this, it's like a simple question is like, I don't know how many days have you spent in this country? If you travel a lot, that can actually be a tricky question.
Right.
And you say like, well, here's my calendar, here's my email. Figure it out.
Well, TzEL shows one side of what can be built on Tezos. Other use cases bring out different parts of the infrastructure. Outside of TzEL, is there anything being built right now that's got your attention as well?
I mean, I took a particular interest in like the post-quantum stuff. So like, there's really interesting techniques for doing adaptability in a post-quantum way, which are actually quite efficient. So I'm looking at that. It's really fun because it's really like like deep core engineering. But there's also activity happening on the app stuff. I'm also like I really like the developments with metals.io, which like are pushing more metals and more products out there. That's quite interesting. It's very different type of work from like the deep nerdy core engineering work.
Well, TzEL may change over time. Later versions may look different from this prototype, but research implementations they help show what part of the problems are real. If later versions look different years from now, what would still make this prototype an important experiment?
Sorry, if what? I couldn't catch it.
If if later versions were to look different than the current
Right.
iteration right now, what would that look like in the future?
Mm, I think they would look pretty similar. I think maybe different proving systems. So TzEL uses work done by Starkware. So Cairo, S2. Uh, and there's a new type of proving systems which are very similar to Stark, which are using multivariate polynomial as opposed to univariate polynomial and different techniques, which are maybe a bit more efficient. And they are part of a project called LeanVM, which is developed in the Ethereum community. So I've been playing with LeanVM. It's very efficient. It works very well. So I think it's quite a it's really good replacement for the Stackware libraries. However, it really focuses on proving. It doesn't do zero knowledge yet. It's doable. It's not a massive like endeavor to turn this like NVM into something that does zero knowledge, but it's not been their priority because it's mostly used for scaling. However, I would say if and when LeanVM becomes useful for zero knowledge proofs, it can be a drop-in replacement. What's interesting is that you're not tied to a proof system. At the end of the day, an encrypted ledger looks like is essentially a Merkle tree of hidden commitments to little nodes. That's what it looks like. And you can use any proving system on top of this. That's the thing. You're not necessarily tied to one. As long as you can prove some statement about like, hey, I know like a pre-image of this hash that has this and this and this property, you can accept that. So you don't have to like you're not stuck with one.
Well, Arthur, I really do appreciate you taking the time out today to share with us and explain this. It's a lot to go over, and it's a lot for the average person. And I think you really did make this a lot clearer for a lot of us. Thank you so much for your time today.
Well, thank you. And like I know we haven't like put out a post yet, but look out for it. You'll be able to give TzEL a try and launch it and play with it. The code is already out there, but there will be a bit of a bit of infrastructure for everyone who wants to play with it to play with it.
Well, thanks again, Arthur, and I look forward to the opportunity to do this again.
Thank you very much.